Chapter 2, Exercise 15. To find the symmetric difference A plus B of sets A and B to be the set A minus B union B minus A. Part A asks us to show that A intersect B plus C is equal to A intersect B plus A intersect C. Part B asks us to show that A plus B plus C is equal to A plus B plus C. Right, so this is kind of a lengthy problem. It took me a while to solve, not in terms of difficulty, just it takes a lot of steps. And with that in mind, I wanted to prove first a couple lemmas that I think were pretty useful to avoid much repeated work and try to keep the proof as short as possible. Right, so the first lemma is going to be that A plus B is equal to B plus A. And this might seem obvious, but it's good to show because sometimes this is not um this is not always the case. It's not always symmetric. It's not always commutative. For instance, A minus B is not equal to B minus A. But I digress. So A plus B is going to be equal to A minus B union B minus A, which is equal to B minus A union A minus B. Here we're leveraging the fact that the union operator itself is commutative, so this tells us that A plus B is equal to B plus A. And the second lemma that I wanted to establish is that A minus B is a subset of A plus B. And this is very obvious, but if you look at the definition closely, but I did want to make it extra clear. So suppose X is in A minus B, then X is in A minus B union anything, and specifically it's an A minus B union B minus A, which is equal to, or rather, which implies that X is in A plus B. So indeed, A minus B is a subset of A plus B. Right, and the last one is gonna be this lemma right here, that X is not in A plus B if and only if X is in A and X is in B, or X is not in A and X is not in B. Okay, so let's do both directions. So let's do the forward direction first. And oh, let me change the color. X is not in A plus B. Then X is not in A minus B union B minus A. Thus, X is not, it is not the case that X is in A and X is not in B. I'll move this over here. Or X is not in A wait. Thus, it is not the case that this, or it is not the case that that. And, sorry. Right. Sorry, my mind just blanked for a second. Okay, so if x is in A and x is in B, wait, sorry. Oh yeah, if and x is in B, then it is not the case that x is in A and x is not in B, and or let's just use this, and it is not the case that x is not in A and x is in B. And then if x is in not in A and x is not in B, then it is not the case that x is in A and x is not in B, and it is not the case that x is not in A and x is in B. Right. And okay. And this is kind of all you need to do. We just need to do it in reverse for the other side of the implication. So it's going to be something like this. Now, suppose x is in A and x is in B, or x is not in A and x is not in B. And we need to consider both cases and show that in both of them, they are not in A plus B. So if x is in A and x is in B, then x is not going to be in A minus B, and x is not in B minus A. So x is not in A minus B, union B minus A. And let me move this to the next page. Therefore, x is not in A plus B. And if x is not in A and x is not in B, then x is not going to be in A minus B because x is not in A, and x is not going to be in B minus A because x is not in B. So, again, so x is not in A minus B union B minus A, and thus this x is not an A plus B either. Cool. All right, so a bit laborious, a little foreshadowing for what's about to come. And you'll see that this lemma, specifically 3, will let us, well, actually all of them, but they will let us skip some parts of the proof. If we ever determine that either of these conditions are true, then we can just conclude that x is not an A plus B and skip that part of the proof. All right, with all that said, I can't keep delaying this any longer. A, what are we showing for A? We're showing that A intersect B plus C is equal to A intersect B plus intersect C. Is that true? Yep, that's exactly what they want us to show. Okay, so we're going to show first that A intersect B plus C, as usual, is a subset of A intersect B plus A intersect C. Okay, so suppose x is in A intersect B plus C, then x is in A intersect B minus C union C minus B. Right. And recall, one second. Let me just take a look at my notes. Yeah. So intersection distributes over union. So A intersect B minus C union C minus B is going to be equal to A intersect B minus C union A intersect C minus B. And there's a proof of this in the book somewhere. And this is all to say that x is going to be in A intersect B minus C, or x is going to be in A intersect C minus B. Right, so what we want to show now is that both of these roots imply, and both of them imply that x is in A intersect B plus A intersect C. Right, okay, so if x is in A intersect B minus C, then x is in A and x is in B minus C. This is what we get from the intersection. And from the difference, we get that x is going to be in A, x is going to be in B, and x is not going to be in C. Okay. So, what we want to show is that here we want to show, if we're trying to show this, we want to show that this is true. Right. So, because then if we have the difference, then we can just turn it into a plus by our lemma 2. Right. So x is going to be in A intersect B, but x is not in A intersect C because x is not in C. So x is in A intersect B minus A intersect C. And by lemma 2, x is in A intersect B plus A intersect C. And let me just put the parentheses. Okay, cool. So that's one of them. And then the second one is the exact same thing. We just have to show, right, so we got rid of this one, and now we need to show this one. Now suppose x is in A intersect C minus B, then x is in A and x is in C minus B, thus x is in A and x is in C, and x is not in B. So x is going to be in A intersect C, but x is not in A intersect B. So x is in A intersect C minus A intersect B. which implies that X is in A intersect C plus A intersect B. And then by lemma 1, X is in A intersect B plus A intersect C. Because the symmetric difference is surprisingly symmetric. Okay, that's one side of the inclusion. And now we need to show the other side. Or rather, let's just conclude. We conclude that A intersect B plus C is a subset of A intersect B plus A intersect C. Okay, and now part 2, as usual, is to show the reverse. So A intersect B plus A intersect C is a subset of A intersect B plus C. Cool. Alright, so now let's suppose X is in A intersect B plus A intersect C. Then X is going to be in A intersect B minus A intersect C. Or it's going to be in A intersect C minus A intersect B. And let me put the parentheses where they belong. There. Okay. So we have two cases. Okay. If X is in A intersect B minus A intersect C, then X is in A and B. But X is not in A intersect C. So X is in A and X is in B, but it is not the case that X is in A and X is in C. But X is, okay, so now we have this right here, but we know that X is in A, and this must be false. So we can conclude. So since X is in A, we can deduce that X is not in C. So X is in A, X is in B, X is not in C. Right. So X is in A, X is in B minus C, and or rather, let's just make 1 point at a time. So X is in B minus C, which implies that X is in B plus C by lemma 2. So X is in A and X is in B plus C. Thus, X is in A intersect B plus C. There we go. And now, if on the other hand, X is in what? A intersect C minus A intersect B. then uh, x is A intersect C, and x is not in A intersect B. So by the same reasoning as above, x is in A, x is not in B, but x is in C. Same exact proof. Okay, so x is going to be in C minus B, which implies that x is in C plus B, which implies that x is in B plus C by lemmas 2 and 1 respectively. So x is in A and x is in B plus C, thus x and A intersect B plus C. Uh, so indeed, A intersect B plus A intersect C is a subset of A intersect B plus C. Thus, we conclude that A intersect B plus C must be the same set as A intersect B plus A intersect C. Alright, and that is all for part 1. But, of course, that was the easy part, and now we need to show part 2, which is A plus B plus C is equal to A plus B plus C. Just to make a remark, what Anderton is trying to show us is that the intersection distributes over addition, or rather, the symmetric difference. Um, and I don't know where this will come in handy, but distributivity is usually nice. A nice property to have. Helps you simplify stuff. Either it lets you break it down, like in this direction, or it lets you, once you have these, something like this, it lets you simplify it in this direction. So distributivity is pretty cool. And this one is different. It's not distributivity, it's associativity. So it's trying to show us that no matter where you place the parentheses, um, it's all good. Which is in contrast to um, the regular difference of sets, which is not associative. Okay, so that tangent aside, let's do part B, just to show that A plus B plus C is the same set as A plus B plus C. Also, my handwriting, it's kind of late at night. My handwriting will get worse, so I hope it's legible enough to follow. If not, then good luck, Charlie. Okay, so part 1, A plus B plus C is a subset of A plus B plus C. So suppose X is in A plus B plus C, then what is this? All right, then X is in A minus B plus C union, so many parentheses, union B plus C minus A. Okay, so this is where things come in handy, specifically lemma 3, because we want to show that X is in A, but it's not in B plus C. So Let's see how it is. All right, so let's do case one. So if x is an a minus b plus c, then x is an a, x is not in b plus c. And then by lemma 3, not gonna lie, I forgot why I wrote down those lemmas, but now I'm remembering. Okay, by lemma 3, either x is an a, sorry, x is not in b plus c if and only if x is in b and x is in c, or x is not in b and x is not in c. Okay, good. So now we have two cases, and we don't have to go through all the tedium of breaking down this set any further. Right, because that took me a long time, and it's not fun, but you can try it. All right, so if x is in b and c, and sorry, and x is in c, then what? Then we want to show that x is in this set. So just to clarify what I'm about to do, we want to show that either x is in a plus b minus c, or x is in c minus a plus b. Given that x is in c, in this case, we want to show that x is not in this set. So, okay, then x is going to be in a, x is in b, x is in c, just reiterating. So if x is in a and x is in b, then x is not in a plus b by lemma 3. So x is in c and x is not in a plus b. So x is in c minus a plus b, which implies directly that x is in c plus a plus b, which implies that x is in a plus b plus c by lemmas, what is it? 2 and 1, respectively. Okay, so that's one case out of the way. Now, if I'm going to start to add a couple more pages because I realized that even though I added a bunch of pages, it's still not enough. 1 second. There. All right. Cool. So that is this branch of the proof done with. And now we need to do the other one. If, on the other hand, x is not in B and x is not in C, then we have x is in A, x is not in B, x is not in C. If x is in A and x is not in B, then x is in A minus B, which implies that x isn't a plus b by lemma 2, right? And then if x isn't a plus b, but x is not in C, then x isn't a plus b minus C, which implies, of course, that x is in a plus b plus C by lemma 2 again. All right, so that's the second branch done. Okay, that is that branch. So now what we need to do is, I'm just gonna write up. So if x isn't a minus b plus c, then x isn't a plus b plus c. Now if x isn't b plus c minus a instead, then x is in b plus c, x is not an a. And now we want to show that this also leads to us arriving at this fact. Okay, if x is in b plus c, then x is in b and x is not in c, or x is not in b and x is in c. This is just by the definition of the symmetric difference. So I've been dreading recording this video for a while, but we're here. So if x is in b and x is not in c, then we have x is not in a, x is in b, x is not in c. Okay, so x is in b minus a, which implies that x is in b plus a, which implies that x is in a plus b by lemmas 2 and 1. Now, if x is in a plus b and x is not in c, then x is in a plus b minus c, which implies that x is in a plus b plus c. Okay, so that's branch 1 done. And now, on the other hand, if x is not in b and x is in c, then we have, my hand is cramping, 1 sec. Writing on paper is so much nicer than writing on a tablet. That's my hot take of the day. Okay, then we have x is not in A, x is not in B, and x is in C. If x is not in A and x is not in B, then x is not going to be in A plus B either. So x is in C, and x is not in A plus B, which implies that x is in C minus A plus B, which implies that x is in C plus A plus B, which implies that x is in A plus B plus C. Due to the usual suspects. Cool. Okay, so there we go. That's one. Branch done. Right. So if x is in b plus c minus a, then x is going to be in a plus b plus c. And it follows that a plus b plus c is a subset of a plus b plus c. Okay, that's one side of the implication done. Now let's do part two before I finally get carpal tunnel. Okay. Uh, suppose x is in a plus b plus c, then x is in a plus b minus c, or c minus a plus b. And this is pretty much the same proof. I mean, all the heavy lifting was done in the previous part, but I'm just doing this for completion's sake. If x is in a plus b minus c, then x is in a plus b and x is not in c. So if x is in a plus b, then x is in a and x is not in b, or x is not in a and x is in b. By the definition of the symmetric difference. Right. If x is in a and x is not in b, then we have x in a, x not in b, x not in c. Since, and I'm just going to skip the annotations of which lemmas we're using by now. Since x is not in b and x is not in c, x is not in b plus c. So x is in a minus b plus c, which implies that x is in a plus b plus c. Okay, that is this branch. Now, if x is not in a and x is in b, then we have x is in not in a and x is in b and x is not in c, right? Mm, yeah, okay. So x is in b and x is not in c implies that x is in B plus C. Uh, so X is in B plus C, yet X is not in A, which implies that X is in B plus C minus A, which implies that X is in B plus C plus A, which implies that X is in A plus C. Cool. Okay, let's branch two. Two branch. Okay. Now, if X were in C minus A plus B instead, then X is in C and X is not in A plus B. So either X is not in A and X is in A and X is in B, or X is in neither. Parentheses for clarity, but I think we all know what we mean here. Okay. Sorry, I forgot to conclude this part. If X is in A plus B minus C, then okay. If X in A and X in B, then uh, X in A and X in B and X in C. So X in A and X in B implies that X is not in A plus B. So X is in what? Oh, sorry. X is in, I got them sets mixed up. X in B and X in C implies that X is not in B plus C. So X is in A, but X is not in B plus C. Thus, X is in A minus B plus C, which implies that X is in A plus B plus C. And that is this branch. Finally, if X is not in A and X is not in B, then X is not in A, X is not in B, X is in C. So, my neck. So X is not in B and X is in C implies that X is in C minus B, which implies that X is in C plus B, which implies that X is in B plus C by our usual lemmas. Thus, X is in B plus C, but X is not in A, so X is in B plus C minus A, which implies that X is in B plus C plus A, which implies that X is in A plus B plus C. So if X is in, what was this set? C minus. Then X is in A plus B plus C, thus x being in A plus B plus C implies that x is in A plus B plus C. So A plus B plus C is a subset. Actually, I'm just gonna skip this one. Bye bye. A plus B plus C is a subset of A plus B plus C. And thus we conclude that A plus B plus C is equal to A plus B plus C. All that for this. I hope you enjoyed the proof. I certainly did not. But either way, I hope it was helpful. And I will see you in the next video. If I didn't scare you off with this one. Bye bye.